Hi Westfield Physics students. This is going to be a short little video to help you out in doing some of your kinematic equation problems. These are some problem solving steps that I used to use with my students so that they'd have a good shot at success. So first off, what we want to do whenever we have a problem, and we're going to go through and we're going to solve some sample problems over here. But first thing we want to do is we want to read through the problem, make sure we understand it, and then go through a series of steps to ensure success. First thing is identifying the knowns. We have to know what we're being told. This information is considered to be valid, good, with no errors in it. The next thing we want to know is, well, what don't we know? What do we need to find out? Sometimes we're being asked, for displacement, acceleration, a time value as part of the problem, but sometimes we're not asked for something, but that doesn't mean that we know it. So a problem could ask you for displacement, but you also don't know the time, and it's important to just identify what you don't know. Then you have to look at your units. It's always important that all of the units agree with each other. If you have a unit for velocity in meters per second and a unit for displacement in miles, it's not really a problem. You just have to go ahead and convert one of those units into the other type that agrees. So in that case, you might want to go ahead and convert miles into meters so that it agrees with the meters per second in your given velocity. Next, it's always helpful to have a little sketch, especially when you're talking about things moving around, and that goes right in line with number 5 in choosing direction. Direction is something that many times is up to you. You can choose the positive direction, you can choose the negative direction. Most of the time, by default, people will say things traveling to the right is in the positive direction and to the left is in the negative direction. They also consider a lot of times up to be positive and down to be negative, but it really depends on the situation, and that's something that's under your control as long as you define it. And defining in the sketch is really important. Next, after you've got all those things done, it's time to select the mathematical model that you're going to be using here. I call it a formula, but it's a mathematical model for the motion that we're trying to describe. And in our kinematic equations, you can see that there are 4 of them. So we'll do some work in going through the 4 of these with our sample problems and determining the right one that would be best suited for solving the problem we're interested in. After that, after you've done steps 1 through 6, really the hard part, the physics part, is done. What you have to do now is the mathematical part. You have to get some kind of answer, either numerical or everything in variable format, but that's the math part. Lastly, what you want to do is, especially most of the time when you get a numerical answer, you want to look at that answer and make sure it makes sense. If you're doing a problem where you're calculating how fast a car is going to travel, and the answer comes out to be it's traveling at a rate of 5,000 meters per second after it goes through an acceleration, unless this is some kind of car in a fantasy world, you realize that's too fast. That probably doesn't make sense. Go back and look and see if you made a small mistake. So let's go ahead and jump into this and try and solve a few problems. The first one that I have here says, at Six Flags Great Adventure, the roller coaster Kingda Ka accelerates riders in a straight line uniform motion from rest to 57 meters per second, which is about 128 miles per hour. And that takes about 3.5 seconds to happen. So it's a 2-part question. First, we want to determine the magnitude of the acceleration, and next we want to figure out how far does the rider travel during this period of acceleration. So we'll go through our steps. First thing I want to do is go ahead and identify my knowns. And in this case, what do I know? I know that we start at rest. So my initial velocity is 0 meters per second. It says right there, from rest. Next, I see that we're going to end up with a final velocity of 57 meters per second. Okay. Now, do I need to do anything with this 128 miles per hour? Not really. It's the same thing as 57 meters per second, and by looking at the rest of my units here, I've got a time in seconds. I want to leave my velocity measurement as 57 meters per second because it agrees with that time value, and that also means I'm going to get a displacement value in meters, which is going to be fine. It doesn't tell me to return a displacement value in miles or yards or any other units, so I'm assuming meters is going to be fine. The last piece of information I can get from what's given is that the time that the acceleration is occurring is 3.5 seconds. So I'll go ahead and put that into my table. I look, those are all my knowns in this problem. What are my unknowns? Well, I don't know what the acceleration rate is, and I don't know the displacement of the riders over that time period, and that happens to be exactly what I'm asked for in Part A and Part B. So I'll go ahead and I can make a little sketch. I could say that, you know, a lot of times sketches like this are very simple. You'd say, okay, I'll start here. This is my initial condition. I have an initial velocity of 0. And sometime later, I've got a velocity of 57 meters per second, assuming to the right is positive. And this is a horizontal motion problem, so I don't have to define any vertical any vertical signs because it's only going to be happening in the horizontal plane. And my displacement would be the distance from there to there. So that would be the displacement for this problem. A simple problem like this, sketch is not as important, but it's good to get into this habit because as your situations get more complicated, the sketches can really help you keep sense of things. So next I'm going to go through and I'm going to select the mathematical model that I want to use. Let's take a look at what we got here. So here are my kinematic equations. I know initial velocity, final velocity, and the time interval that this happened over. I don't know A and D. So recall that for these equations, I need to choose one where I know, or I have quantities for all the variables except for one. So in part A, I'm solving for the magnitude of the acceleration. So I want to choose the kinematic equation that, number one, it has A in it, because that's what I'm going to try and figure out. But I also need it to, all the other variables, I need to know those. So those are the two things I'm searching for here. An equation that's got A as one of the variables, and as long as that equation, I know everything else, that can be the equation that I choose. So I look at the first one here and I say, okay, do I know the final velocity? Yes, I do. Do I know the initial velocity? I do. There's A. And do I know the time over which it happened? Yeah, I know that. So that equation's looking really good. So I'm thinking the first one is one I can use to solve for A. Let's just take a look at the second one, see if that would work. Well, do I know the displacement? I don't. So that's a problem. I know the final velocity, the initial velocity, and the time. Well, this equation also, it doesn't even have acceleration in it. So obviously I can't use it to solve for acceleration. But I could use it to solve for displacement. I'll keep that in mind. Coming down to the third equation, I don't know displacement. I know the initial velocity, I know the time. There's A, that's what I'm looking for, but I don't know it, and it's got time. So this equation, it's got A in it, but it's got two unknowns. And I can't solve this equation because it's got two unknowns. And a similar situation down here, while I know the final velocity and initial velocity, I've got those two unknowns. So in order to solve for the acceleration, the only equation that's suitable right now is this one. Final velocity is equal to the initial velocity plus acceleration times time. And the next thing I'll want to do is I can do some algebraic manipulation, and I will rearrange this equation to solve for my acceleration. And then I'm going to go ahead and put in my known values and solve the problem. At this point, this is just an exercise in mathematics. It's really important to make sure that you keep the units throughout your problem, because if you pay attention to the units, they could help find an issue later on. For example, if I got this algebraic manipulation incorrect and I solve with my units later, I might be able to see that because my units wouldn't work out. And if my units don't work out, that's an indication I made a little boo-boo someplace in moving around my variables, and then I have to go back and look at that. So Now I just go ahead, I put this in my calculator. I've got 57 meters per second over 3.5 seconds. Let's see, I've got two significant digits here. We'll assume that the 0 is 0.0000, but I've got 2 sig figs there, I've got 2 sig figs there. My answer should have 2 sig figs, so that's going to be about 16, and my units are meters per second squared. So that's the acceleration rate for that ride. Okay, in part B, what am I looking for? I'm looking for how far does the rider travel while they're being accelerated. Okay, so I just have to go back, I have to find a suitable equation and do this process again. One thing I might be tempted to do is to choose an equation such as this last one right here, because I know final velocity, initial velocity, and now I know acceleration, or at least I think I know acceleration. And I could use that equation to solve for displacement. I could do that. The only potential problem with doing that is I calculated that value for acceleration. If I made a mistake, the value that I calculate for displacement will absolutely be incorrect. So it's really good practice whenever you can to stick to these known variables, these variables that you were given, because somebody gave you those. You know that those are reliable. You know that you can use those in your mathematical models, and as long as you do everything right, you'll return an answer. This is also a way to check your work. You could go ahead and solve for the displacement using your known variables, and then do it again using, and solve for displacement again, but this time choose an equation where you have to put in the variable that you solve for, and if you get the same answer for both cases, then that's your double check and you know you did it right. But in this case, I'm going to stick to my knowns, and I'll look and I'll say, can I use this equation? No, it doesn't even have displacement in it. Can I use this equation? Let's see, there's displacement, final velocity, initial velocity, time. Yeah, I can use that one. Can I use this one? No, I've got 2 unknown variables. Same thing here, I've got 2 unknown variables. So it looks like my second equation is going to be the way to go. And in that case, the displacement is half the sum of the velocities times time. And I just go ahead and what they refer to sometimes as plug and chug. But basically all I have to do now is work out my math. And if my math works out correctly, I'm good to go. Made sure to follow my units through, and I get that my displacement, let's see, how many significant digits am I working with here? I'm still working with 2. That'll come to about 96 meters. Let's see, do my units work out? Meters per second plus meters per second is meters per second. Times second will cause the seconds to drop out, leaving me with a value of meters. I know that's my correct value for my correct unit for displacement. I won in this case, and I'm good to go. And I could always go ahead and do some unit conversion. 96 meters times, let me see if I can get this from memory. I believe it's 3.28 meters, or I'm sorry, feet in a meter. And if I do that, that comes out to about 315 feet. Which seems very plausible to me. 315 feet that you're being accelerated over on this roller coaster. Sounds about right. So, all right. Hopefully that was fairly straightforward for a straightforward problem.